Okay. So I think we can start. So what have we done? So last time, we started talking about normal rings, right? Normal rings. So by definition, you can give a very down-to-earth definition, which is that, well, it is a local condition if you wish. So it means that when you look at every single local ring, it is integrally closed. It is integrally closed. Okay. What does this mean? It means that it has to be an integral ring, first of all. And so it has a field of fractions. And so what this means is that when you compute the closure of Rp, what does that mean? You take the element x in the field of fractions of this ring, right? And you look at those satisfying monic equations. Monic equations over Rp, right? So AI is in Rp. So in a first commutative algebra class, or just an algebra class, probably you saw that this thing here inside KRP is a subring. Is referred to as the integral closure of Rp or the normalization of Rp. And so being integrally closed means that the equality is just, but the inclusion is equality. Okay? So this is the definition of normal ring. But we have the graphic version, which is due to zero, which means that this is simply R1 plus the famous S2 condition. Okay? So this means, remember, regular in codimension 1. So this means that if you look at the singular locus of the ring, the singular locus is small. It has to have codimension at least 2, right? So for example, if R represents a surface, then the singular locus have to be made of isolated points. Or if R is some sort of threefold, how do you draw a threefold? Let me draw a sphere, I guess. Then the singular locus have to be made of lines or points. You know, that's what it means to be regular in codimension 1. The singular locus cannot have a codimension 1 component. Okay? And the S2 condition, well, we saw that it is defined in terms of depth, but intuitively, or roughly, it means that when you look at those points of codimension 0, 1, 2, they have to be Cohen-Macaulay, right? So in R1, you have that the codimension 0 and 1 point have to be regular. S2 adds that the codimension 2 have to be Cohen-Macaulay. But moreover, it also says that for codimensions 3, 4, 5, 6, and so on, the depth is at the very least 2. Okay? So these two conditions together imply, let's say that, so you have to look at codimension. You look at codimension 0, codimension 1, codimension 2, codimension 3. Remember that codimension is synonym of height. So to say that the codimension of a point is n is to say that the height of the corresponding primary ideal is n. But then codimension is slightly more geometric. So So you look at all possible codimensions. So if you look at codimension 0, you have regular. If you look at codimension 1, you have regular. If you look at codimension 2, you have cohomacolic. So regular implies cohomacolic. But here, at the very least, what you have is that the depth is more than 2, depth is more than 2. Okay. And so that's what you get in a normal ring. So for example, you see that if you have a curve, then it has to be regular if it is normal. If you have a surface, you have a cohomacolic thing. And beyond that, well, you have normal. But also we started to study what S2 means, and we saw that what S2 really means is that you only have to worry about the dimension 1 information. Okay? So more concretely, we wrote down the following, and actually made a mistake that I would like to fix. I wrote something like this. We said, okay, let's take a ring, and let's look at the math between S2 modules. Okay, so I said that if phi is either injective, I think I said surjective, or an isomorphism in codimension 1. This means that when you look at what is happening locally at every point of height 0 and 1, you have an isomorphism. Then let's call this phi. Phi is respectively injective, surjective, isomorphism. So what is wrong here is that this is not true for surjective. They clarified in the notes, okay? So you can check injectivity, and well, the property that we want is isomorphism in codimension 1. So if you're dealing with S2 objects, all you have to worry about is what happens generically and on prime divisors on a normal ring. That's the moral of the story, which is wonderful, right? Because in principle, you have to worry about all possible points, which could be extremely difficult. But when you are dealing with S2 objects, all that matters are codimension 1 information. And the second component of a normal ring tells you that codimension 1 information is wonderful because you're working over regular rings, no singularities. Okay? So this is what this theory is telling you about normal rings. And you see that it's wonderful, right? Because you may think naively that this tells you a lot, but this is hard to play with, right? What do you make out of this? Not much, right? But here you have something very concrete that looks like more advanced, but actually it's telling you something very explicit. It's something you can play with, something that is actually useful. Okay. So that was the discussion from last time. And then we introduced the concept of divisors. We said that a divisor is just a bookkeeping tool. Okay, it's more about predictability than mathematics. Okay, it's just the formal sum over prime divisors. Because this theorem is telling us, right, like what matters is codimension 1 information. And so we want to keep track of the codimension 1 information, and we do that using divisors. We look at every single prime divisor, meaning a height 1 prime ideal, and we look at some integer there, or it could be over any other ring, really good. So we put that information here. Okay, so that's a veiled divisor. So if you look at the definition, a veiled divisor doesn't tell you much. So the other day, what we did was, at the very end, we started talking about modules you can extract from divisors. So let's now start over there. So if you have a divisor, so now we are talking about our We also saw that if you have a normal ring is a product of integrally closed domains. So we can always work with domains. It's the same thing as having a variety that whose irreducible components are connected components, and you can just focus on one connected component, right? Because you can do one at a time. So let's take a normal integral domain. So here we have a divisor, and out of the divisor we can construct a meaningful object, which is the following. So we're going to define our D to be, by definition, the element of the units of K, the group of units here, such that when we compute the divisor of F and we add D, we have an effective divisor. So let's look at this. Recall, the divisor of F is by definition just looking at the evaluations of F at the prime divisor. Remember, because it is regular equidimension 1, every equidimension 1 point gives you evaluation. That's the evaluation we're looking at here. So we just compute that. And so you think of this, if it is positive, you think of F vanishing on P with certain order. But if it is negative, you think of that as a pole. Okay? And so when you look at this object, well, we have to add 0. We said that. So this lives inside K. It is an R submodule. So this is an R submodule. Actually, let's check if this is an R submodule. Let's do a proof. Just to make sure that we understand the definitions here. So what does that mean? So let's take F in here, and let's take R in R. So in principle, for example, we have to prove that R times F is in here. Right? So let's check that. So in principle, we have to check whether or not the divisor of R times F plus D is effective. That's the question mark. But then we know how to compute it, right? This is going to be a divisor of, because this is a homomorphism for the multiplicative group of K and into the divisor class group, so we can separate this. Now here I'm slightly hesitant because I can only compute this if R is not 0. So, well, if R is 0, this is 0, so it's in here. There is nothing to do. But otherwise, you can separate some, and you get that. And so by hypothesis, F is in here, right? So this is effective, but the divisor of any regular element is effective. An element of R can only vanish on R. It's a regular function, right? So we were saying the other day that you can think of K as the meromorphic functions on this on the spectrum of R, and R are the regular functions. So the holomorphic function can only vanish, and so you have the sum of two effective divisors is effective. So you can see that it is closed under scalar multiplication. And well, you would also have to prove that it is closed under addition, and for that you would have to take the evaluation of F plus G, but then you use the property of evaluation that is it is more than the minimum of the corresponding evaluations, and so you always get an effective thing. So I'll let you do that as an exercise, the rest. Okay. I just wanted to recall a few things about this function. So this object here is a submodule of K. Intuitively, you think of it as those metamorphic functions with prescribed poles and zeros. The prescription is given by D, right? So let's look at some properties, which, as you may expect, are all exercises for you. Properties. Here I'm talking about exercise 5.33. What are the properties of this thing? First of all, this object here has rank 1. So why is that? Actually, more generally, you can look at how this object localizes. And it localizes the way you expect. If I take a prime ideal of R and I localize, what I get is essentially RP dP. Let's look at what that is. So RP, the localization of RP and R, they share the same field of fraction. So this doesn't change too much. And so we're looking here, let's say now divisors of RP of F such that dP is more than 0. And what is dP? Remember, dP is just a formal sum. And so when you localize the point, what you do is that you just get rid of those P that don't go through that point. So you just make your divisors smaller. So if you what is computed the rank? The rank is going to localize at the prime 0, right? And so what happens when you localize at the prime 0? Well, there is no prime divisor going to 0. So the divisor here becomes 0, the 0 divisor. And so you would be just looking at the elements of K whose divisor is positive, which is all of them. So the localization, literally, so the point is that if you do this, if you localize this at 0, you literally get K back. You get all functions. Okay? So, but I'll let you think about the details. It's an exercise. The second property, and you start to see the magic of this. Do it down here. The second property has to do with computing the dual of RD. So let's say you want to compute this dual. I'm claiming that there is a canonical map from here to here. What is it? Well, if you take F in here, I'm just gonna go ahead and define a map. I have to define a map that goes from RD to R. So I have to take G and send it to an element of R. What do you think is going to happen here? It's going to multiply. But let me do it in the other order. It's going to be F times G. So in a sense, this map here, I'm going to send F to the map that is just multiplication by F. And we can check that this is well defined. Because for this to be in R, we know that this divisor has to be effective. Let's do that. So the divisor of Fg is the divisor of F plus the divisor of G. But the divisor of F, because it is in here, is more than D. And the divisor of G, because it's in here, is more than negative D. So make it 0. So you have a well-defined R linear mapping here. An element of here defines an element of the dual of R. And what do you think is the conclusion? This is an isomorphism. And how on earth do you prove that? If you just try to prove this is an isomorphism, just by showing this is bijective or whatever, you will fail. Well, it's easy to, well, it's not so hard to see that this is injective. But how do you prove it's subjective is the question. How do you prove that any map here comes from a map here? So doing that is difficult. If you just try to do it just by proving that it's subjective, you give yourself a map here and try to construct a map here, you will fail. If you can do it, I'll give you, I don't know, what is a good amount? I don't feel like giving money, but like 100 pesos. I give you a coffee, I buy you for a coffee. If you can do some brute force, how you do it? What do you have here? A map between what? Well, actually, I think I don't know how to do this into the right order. So, okay. So the point is that the way you should do this is to notice that this is reflexive. So the whole module. I don't know if I said it last time, but it's in the notes for sure, that if you hum into R on a normal ring, you always get a reflexive module. How do you do that? Because you can write down a presentation for RD, and when you dualize, you show that this is going to be a submodule of a free module whose kernel is inside a free module. And so that should let you conclude that this whole module here is S2 actually. It's not just reflexible. What you get to prove is that it is S2. Okay? So the injectivity here is fine. That I find you can do. And so you want to prove surjectivity. And to do that, actually, the whole point is that you can do a codimension one. I guess it's related to the remark I was making there. So the point is that what you want to do is that you want to prove this in codimension one. Okay? You want to reduce the case in which you work in codimension one. And then RD, it becomes trivial. It's just R. And the statement is trivial. Right? If you take RD and you localize the prime divisor, well, this becomes R. I guess that's part of the exercise. And so this object here is very trivial, and this is just R. This becomes R, and the isomorphism is obvious. Okay, this is part of the business here. Like you want to be doing things in codimension one, and then you exploit that your objects here are S2 to do that essentially. So part of the conclusion here is that by doing this, I guess I put it here as part of B. B, the conclusion is that RD itself, well, you can replace D for R minus D. This object here is reflexive, i.e. S2. Right? Well, I guess that was part of the other day to see that on a normal ring, being reflexive and being S2 are the same thing. So what do we know so far, essentially? That whatever this object is, has rank 1, and it is reflexive. Okay? which is not surprising because what this is supposed to tell you is that this object here is determined for dimension 1. It only has the dimension 1 information, and it is rank 1 information. Okay, for dimension 1, it is locally free of rank 1. It's an invariable object if you use the language of algebraic geometry. Okay, so let's think of more properties of this object, this RD. Oh, by the way, these RDs go by the name of fractional ideals too. If you look at very classic terminology from Dedekind and more people, it's a fractional ideal. Or people also call it a divisorial module, because it is a module constructed out of a divisor. Okay. So what else? C. The other property is that a divisor is effective if and only if R negative D is an ideal. If this is an ideal, is ideal. For example, this is D. If P is the prime divisor given by a prime ideal of height 1, then you can compute what R negative P is, right? But P is effective, right? This is effective if it gets, right? It's just 1 times P. What do you think is R negative P? What are those functions vanishing on P to order 1? Just P. So very often we're going to stick to this geometric notation and we just extract the ideal out of this operation. Okay? Right? Just, yeah, this, by definition, these are those elements whose divisor is bigger than P, meaning those F such that the evaluation of F at P is 1. And those are the elements of P. Okay? So let's see, let's keep building intuition about these operations. What is the next letter? E? What do you think is R of a principal divisor? What should this be? Let's see. This would be the G's in K such that the divisor of G plus the divisor of F is effective, right? By definition. But what is this? This is just the divisor of G times F. And so I'm asking for G times F to be effective. But this means that G times F has to be equal to R for something in R. In other words, G is just R divided by F prime, sorry, by F, sorry. So what is the conclusion? That whatever this is, it has to be equal. It is R times F inverse inside K. It is just the R submodule of K generated by F inverse. Okay? So in principle, these are all simple things to deduce. Actually, conversely, so what is what we see here? We see that if we take R of div, what we get is a principal, a cyclic R module. What about the converse? Conversely, G, what is, it's F. Conversely, if RD is isomorphic to R, then D is principal. Well, if it is isomorphic to R, it is because it has one generator. And so it turns out that D is just the divisor of that inverse. Okay? Actually, more generally, if we have that RD1 is isomorphic to RD2, abstractly, as R modules, this happens exactly what do you expect? If and only if D1 is linearly equivalent to D2. So isomorphism on this side translates to linear equivalence on the more computational side of these objects. Okay? Yeah. Well, remember what this means, right? Just as a recall, this means that the difference between D1 and D2 is principal. Any questions so far? Just this is the basic properties of these objects. So let me throw in a definition real quick. Definition: a divisor D is Cartesian if D, well, it is a rank 1 reflexible module, and a rank 1 S2 module. So what that means is that it is in codimension 1. It is free of rank 1. So I'm going to say that it is Cartesian if that happens everywhere. If this is invertible. i.e., locally free of rank 1, i.e., flat. I mean, this is what it means if it is flat. That's the definition of Cartesian divisor. Actually, that's an exercise that I didn't write here. You can prove as an exercise that this means that it is locally principal. Look, divisors for which RT is locally principal are Cartesian. Geometrically speaking, it means that locally D is cut out by one single equation. That's the intuition of a Cartesian divisor. Another definition, Picard group. So notice that principal divisors are Cartesian. Therefore, you can take the quotient of Cartesian divisors, modulo principal divisors, and that's the Picard group. So the Picard group of R is by definition Cartesian divisors so let me just say this, modulo principal ones. And so this sits inside the divisor class group as a subgroup. It is a group of the divisor class group of those divisor classes of Cartesian divisors. That's gonna come up later. Okay, now let's get serious here. That's a abelian groups. As abelian groups, yes. So this is an abelian subgroup of the divisor class group. So actually, there's an exercise over here to can prove that, and that they coincide. You know, this modulo this is 0 if and only if your ring is so-called locally factorial, meaning that all local rings are unique factorization domains, for example. Okay, what do we see? So the moral of the story is that we have the group of divisors, and we have a mapping to reflexive IES2 are submodules of K of rank 1. Rank 1. Right? The mapping is that if we have a divisor, you map it to RG. And so what I claim now is that this is a bijection. Okay? And so this bijection is very important because what I want to emphasize here is that over here you have the computational side. And over here you have the conceptual side. Okay? So you want to go back and forth. And here the computations are very easy because this, boils down to adding divisors. And how do you add divisors? Adding integers, 5 plus 3 and things like that. So things that would be very hard here to do, like tensor products and things like that, I'm going to translate into just adding integers over here. Okay? So, but for that we need the other side. How do you go from here to there? So let me take an object here. I'm going to call it I, but this is a j. Let me call it I, and this I here is supposed to be a fractional ideal. By definition, this is a fractional ideal. A fractional ideal is an R submodule of K that is reflexive. Often you saw that for Dedekind domains without center flexibility, but I think it's because in that case it's automatic. But when you go beyond that, you need to add in reflexivity. So how do you do this? How do you construct a divisor that completely determines I? And again, you see the point. The point is that an object here, because it is reflective, S2 is uniquely determined by codimension 1 information. So how do you do this? So we have to construct a divisor. Let me call that divisor DI. Okay? And so at every single P, I have to give you a number. Okay? So let's look at how we construct a number. So let's take this item, okay? And let's go and localize it at P. So this is an RP module. What is RP? RP is a discrete valuation ring. In particular, it is a principal ideal domain. And what is the structure theorem for principal ideal domains? It says that this is going to be composed in between a free part with certain rank plus the torsion part. But this lives inside K. So it cannot have torsion. So it's definitely not torsion. But the rank is 1. So this n has to be 1. So when I localize at P, this is principal. So this equals, it's isomorphic, but let's write it down. IP equals RP times any generator. And generators will differ by a unit. of RP. Therefore, they all have the same valuation. So I can just go ahead and I'm going to just keep track of that. What is the valuation of that generator? And that essentially is information about what this module is. Modules over DDR are characterized by whatever is. Well, rank 1 modules over DDR are characterized by what is the valuation of the generator. That's all you need to remember. And that's what we're doing here. We're just remembering that. And that's a divisor. And I guess what I'm going to leave as an exercise, because we're going to slowly do it, is that if you go from here to there, this is an image of 1 module. Okay? Yeah. Well, actually, there is one direction that is truly trivial. What is it? If I take a divisor and I compute this and then I compute the divisor back, yeah, it's trivial that I get D. That has no science. It's just definitions, really. The other one is the interesting one. If I start here with I and I hook up this divisor and then I try to reconstruct the module that relies on this guy being reflexive. Right? Because, there will be a canonical map which goes like this. So, yeah, if I have if I compute R of DI, this is inside I. But then you want to prove that as an isomorphism. If you try to do it by brute force, you will fail. What do you have to rely on? Reflexivity, that it is S2. And all you need to do is to check that it's an isomorphism in codimension 1. When it would be trivial. So you have nothing to do. You know, the other day I said, like, I used to go to my advisor trying to prove things like that. And I'm trying to prove that it's an isomorphism. I spent a week on that. And the answer was like, have you tried to reflexify? Because once you reflexify, this becomes an isomorphism. But since it's an S2 modules, then it is an isomorphism to start with. Okay. So I'm telling you this because I've tried before to prove things like that are isomorphism by brute force. And I just failed pathetically because I didn't use the S2 property properly. And it wasn't just me, but other students too. Struggled with the same thing. So if you go through the exercise and notes, and you're struggling with something, ask yourself, have I reflexified today? And that will be the answer to it. Okay? So, okay. Divisors equal that. Okay? And so this is why divisors are useful, because they happen to be equal to that. So divisor is just a convenient way to express what this is. Okay? You know, it's another way to, so by analogy, you know the equivalence between matrices and linear transformations. You know, the linear transformation are the things that have a taste, right? So it has a geometry where we can do things. But matrices is where we can do computations, right? And so it's a similar picture. These are the matrices and these are like the linear transformations. Another way to think about it. Actually, more generally, and this is now proposition 535. If you have any reflexive R module, remember this is just S2 of rank 1. any in the world. So you can embed it inside K. This is the part that it has rank 1. Since it has rank 1 and it is torsion free, how does this work? So you can consider the canonical map, that is just that. Since it is torsion free, because it is S1, this is injective, and because it has rank 1, this is K. So it is inside K. And therefore, it is isomorphic to RD for some divisor. This divisor is not unique canonically in no way because it depends on identifying this tensor product with K. And that's another way to say that you have to choose a generic generator. So up to the choice of a generator, like this is unique. Okay? And so okay. The such divisor is unique up to linear equivalence. So D, let's say unique up to linear equivalence. You see the importance of linear equivalence, right? It's just the counterpart of isomorphism, the category of our modules. Moreover, this divisor is Cartier if and only if this is invertible. So let me write it down over here. It's invertible, union flat, if and only if D is Cartier. So, and moreover, I love these equalities because they show my point of what I was saying here. That one side is easier than the other one. Well, this is going to be exercise 5.34 for you. And so there is a map here. The problem. If I have this is like, so let's do the math. So if I have that F1 is more than D1, and that the divisor of F2 is more than D2, right? If we add them together, this means that the divisor of the product more than. So this map is well defined. Is it isomorphism? Very much not. And you should be suspicious because this is reflexive, but this one is not necessarily reflexive. So what is happening is that this object here is a reflexification of this one. So the exercise is that when you reflexify, this is an isomorphism. And so look, here you have fundamental operations between reflexive modules of rank 1. This is actually the product of them. And they become easily the addition of divisors. So that's the point I was trying to make. Very often, you have to compute this. But this is hard. Computing tensor product is not easy, first of all. And now you have to reflexify. Double home. But what is? All you had to do to start with was adding divisors, which boils down to adding integers, which is the first thing you ever learn. Okay? So, The other one we are going to use a lot. By the way, and also further, if let's say D1 or D2 is completely symmetrical, is Cartesian, you don't need to reflexify. Because if one of them is Cartesian, then this tensor product is automatically reflexive. Because one of them will be locally trivial. And the property of being reflexive is local. So locally, if this is Cartesian, this locally this is isomorphic to RB2, which is reflexive. And the other one that we're going to be using quite a bit. You see where so good. Feel free to ask questions. It is to understand this very well. And look at the other one I wanted to mention. Well, let me look at this. So here, this is something you want to know. Suppose that you're given two conceptually rich reflexive rank 1 modules that you just wrote down as divisors. Okay? And you want to know the hum between them. That's an important thing to do, right? That's what algebra is all about. All you have to do is to compute the difference between the divisors. D2 minus D1. Again, just subtracting integers. And you can be very explicit about what this is. If you have a function here, then you can send it to the function, which is actually multiplication by f. Which is the function that takes an element here, that we write down as f1, let's say, and it sends it m side f1. So any mapping from here to here is just the choice of a map from here to here. And there's a canonical map that goes from here to here. How do you prove this is isomorphism? You exploit that they are S2. And then you reduce it to the codimension 1, where everything is absolutely trivial. Okay? But you have to rely on the S2 property. Okay, that's all good and great. Have we encountered so far any module that is potentially interesting that happens to be a rank 1 and S2? The canonical module, right? So recall, well, so let's take R, let's take it to be a normal integral domain, admitting a canonical module. Recall omega R as rank 1. Why does omega have rank 1? Because when you localize it at every point, it has to give you a canonical module of that local ring. So if you localize it at 0, at the 0 prime, at the generic point, it has to give you a canonical module of what ring? Of K, which is a field, it's as regular as it gets, and so it has to be isomorphic to K. And actually, we saw the other day that omega r is S2 as long as this ring is S1. So you have these two properties. So omega r is reflexive because on a normal ring, these two notions happen to be the exact same thing. In particular, omega r is r some divisor, and that divisor is denoted by kr, and is referred to as a canonical divisor. Any divisor that satisfies this is a canonical divisor, but it is unique up to linear equivalence. So you cannot quite say the canonical divisor, you have to say a canonical divisor, and they're all unique up to linear equivalence. In other words, what is unique is the divisor class. Okay, so this is a canonical divisor. But people say the canonical divisor very often. I guess we're going to see why. Because in the context of variety, there is a certain canonical choice you can make. Okay, and so a canonical divisor is any divisor for which this happens. By what we just did today, there has to be one. Okay? And they're all unique up to linear equivalence. So again, a canonical divisor is any divisor in the world for which that happens. That's it. It's the computational counterpart of the canonical module. So that's a canonical divisor, and it's unique up to linear equivalence. i.e., what's unique is the canonical divisor class. Question. Actually, I didn't here. I should put it. Did I? Question: when is the or a canonical divisor, or all of them? If one is all of them are Cartier. When is KR a Cartier divisor? I should add this remark. Any guess? Exactly. Question. When is KR Cartier? Well, the answer, if and only if R is garnishing. And that's why, well, a lot of why the garnishing hypothesis shows up in algebraic geometry, because it lets you conclude that the canonical divisor is Cartier. It's locally trivial. It's locally put out by one single equation. It's easy to handle. It can be pool-like across any morphism and so on. So let's throw in a definition. R is Q-garnishing if let's say if there exists n, well, a positive integer, well, different from 0, let's say, such that n times d is Cartier. Okay, so in other words, when you look at, well, you can let me just write down like this. And the smallest integer, such as this is true, is referred to as the Gordian index of the divisor. So Q Gordian rings are going to show up all the time. So it's good to have them around already. And let me give you a recipe of how to cook up a canonical divisor in geometric context. We will be using it because for us, we always assume that we already have one, and we just play with it.
Does that mean that n is the torsion?
The torsion, n kills the torsion.
So, I mean, ND. So, I mean, you have the free part and the torsion part, and then the free part was rank 1.
The free one of what? Of the divisor class group? Yeah, the divisor class group, well, if it is finally generated, it has a free part and a torsion part. So the canonical class, if it is finally generated, it's going to have a free component and a torsion component. Yeah, I don't know because I'm not. I mean, I don't know where the Picard part, you know, like how does it sit here, right? Like the Picard group's inside here somewhere. So what this is saying is like the divisor class is here somewhere. If I multiply by n, I'm going to land inside here. But if I write down the Picard group, I'm not sure exactly where it's going to live. But if R is local, actually, I know that the Picard group is 0. For example. So in that case, being Cartier means being 0. So in the local case, this means that the divisor class is torsion. Yeah. I guess this means that the divisor class is locally torsion. Yeah. So. Yeah, locally is torsion, and so actually it also means that there are tricks to get rid of it, to make it trivial after some secret cover type object, finite cover. They'll become out eventually, actually. So that's the advantage of having a Q-Gordian ring, that you can almost get rid of the lack of Gordians. So just a remark on how you do this thing on a variety, because you will see it in papers and so on a lot. So let's say that R is essentially a variety, so it's essentially of finite type over some field. So what this means in particular is that when you look at the Keller differentials, so if you don't know what this is, just take a little break for 3 minutes. So you can look at this omega, and since it is essentially a finite type over a field, this is finitely generated. Okay? And actually, since my ring is normal, I'm still assuming this is normal integral domain. So all this means that R is essentially the right. Okay? And so I have this object, and I can go ahead and restrict to the regular locus. Let me call that new regular locus. Regular locus. Which is a big open. It contains all the dimension 1 points. And so this is going to be locally free. Or finite rank. In fact, the dimension of rank dimension of R by the Jacobian criterion if you want. And so then I can compute the determinant of that. So I can compute the top wedge of that object that I'm hooking up here. And I can define omega r tilde to be this object. And so this is going to be an invertible, technically speaking, an invertible sheaf from U. Okay, and then I can push it forward, I can extend it to R. Okay? And so I can define omega r to be the unique reflexive rank 1 R module such that when I take omega r and restrict it on U, I get this omega r tilde. Okay? And so that's often when you are dealing with a right is the way you define omega r. So you have certain canonical choice here because it doesn't depend on anything. This object is as canonical as it gets. So you can restrict it to the regular locus or to any big open. You can hook up this object, which, well, to that you can attach a divisor, and that's often referred to as the first chain class of the already. Okay, it's just a determinant of this object, and then you can just extend it uniquely to that, and that's your canonical divisor. In other words, the canonical divisor here would be any divisor whose restriction to the regular locus is the first chain class of your variety. So when you have in this very specific setup, you have a very concrete way to hook up canonical divisors. But we are often not working in this particular setup. So for that reason, we say, okay, let's assume that we have a canonical module. That we already know that by abstract reason, that's equivalent to being finite over some borders in algebra, which these things are. These things by the net normalization theorem, if you want, they are finite extensions of the polynomial ring. After localization or so. Okay, just a remark telling you that often you will see omega r defined like this. And so it's a more concrete object, and the canonical divisor will be the one defined out of that. What happens is that for us, to study singularities, we only want what the canonical divisor is local at every point. And in that case, whatever your definition is, they all will agree. Because the difference between them is a Cartier divisor, and Cartier divisors are all trivial at every single local point. That's the point. That's the punchline. Okay. So that's something I wanted to say. How much time do we have left? This lecture will hour and 20 minutes are very tiring. Are you used to them? Are you used to teaching like for hour and 20 minutes?
Well, you can cut anytime.
So actually, but let's talk about full factor divisor. So, well, to summarize, all I want to do is define this canonical divisor on a normal integral domain, and that's how you do it. So it is the computational counterpart of the canonical module. I guess in the 10 minutes that we have left, I can give you a sketch of what we're going to do next time instead of starting from the beginning of why this is useful. So what are we going to do next time? We're going to do this Schwitt's correspondence. So we saw that by abstract reasons, sorry. If I have, now let's look at the functoriality of the whole business. That's the point. So if you have a finite extension, so we have a canonical module over here, a canonical module over here. Now F is the corresponding map on spectrum, okay? And so we saw that we have a trace associated to canonical modules. In this trace, by Grothendieck-Godrej, by abstract reasons, we saw that it has a property of generating this thing. So here from S to here, this is one to the trace, and this is an isomorphism. In other words, the trace is a free generator for this Helm set. Okay. And so so what we're going to do is that we're going to exploit this fact. So we're going to take
so that isomorphism is Grothendieck duality?
Yeah. Yeah. One reason why we value omegas is because we understand very well where this Helm set is. It's just trivially generated by the trace, the Grothendieck trace. That's the punchline. But then we can translate that to understand any other map between any other thing in the world. So actually, I can put here S twisted by the canonical divisor of S plus any divisor E on S. And I can put here R, K, R, D. And what we're going to see next time is that this is an isomorphism, but I'm going to tell you that you can think of it as equality on the nose to S by the same principle, actually. How is it? E minus something I have to explain to you. I meant to do that today, but we went pretty slow today. Minus the pullback of D. Yes, this is what this is. So now let me replace E. What I want to do is to replace KS and KR. So that means that I need to put E equals E minus KS. So I'm going to have KS here. And I'm going to have to replace D minus D. Sorry, D for D minus KR. And so here I'm going to have plus the pullback of KR plus the pullback of D. Okay. And so this is a so-called relative canonical divisor. So I'm just going to put a negative KSR. And so you see that what I gained was a way to understand any map in between divisors. They are all the same thing as given an element here, an element of, let me write it down again, S E minus pullback of D minus the canonical class of R. Let's take it simple. Let's take it just E and D to be 0. And so I'm trying to understand the map from S to R. And what you see that any map from S to R is completely determined by the relative canonical divisor of the finite extension. Let's just take an example. Let's take the case of Frobenius. Frobenius is a finite map, finite extension in this case. And what do we have? We have what I wanted to tell you from the very beginning. We have that home just take F to be the iteration of Frobenius. This is going to be R minus the relative canonical divisor of Frobenius. And what is that? Well, it is negative. What did I say? It's the pullback of Frobenius of the canonical class minus the canonical class. So what is the pullback of Frobenius? It's actually just multiplication by Q. Something we're going to see next time. And so when you do the math and everything, what you get is 1 minus Q, the canonical class. And that's it. That's the punchline of this couple of weeks, or this week at least. I think we started with this last week, right? Yeah. It's just that this object that determines F-singularities is the exact same thing as that. The canonical divisor knows intrinsically about this home set. Therefore, it knows everything you need to know about F-singularities. It's a wise object. Okay? Through the trace, actually. Through the trace. We're going to make that very explicit next time. And just to finish, this means that a map P, a potential Frobenius splitting, is the same thing as an element of this. An element of this is just a defect. It's an F such that 1 minus Q KR is effective. So actually, I'm going to call that effective divisor the divisor of that P. Okay, so you can make an interpretation that this P is the same thing as an effective divisor, such that dP is linearly equivalent to 1 minus Q KR. Or let me just say, such that this Q minus 1 KR is linearly equivalent to 0. But I don't like that. So I'm going to divide by that, by this object, and I'm going to talk about Q divisor. That's why the Q divisor formalism show up. But this is not just any Q divisor. It's a Q divisor of 10 divided by something which is prime to P. So this is a ZP divisor in order to equivalent to 0. That's the object I want to look at. So we're going to do that on Tuesday. On Tuesday, we're going to use all we have seen to see that a phi is the exact same information as a boundary, as a delta phi, a ZP divisor, effective ZP divisor, such that when you add it to the canonical class, I'm sorry, people of Zoom, you get 0. And that's it. That's so-called Schwitt's correspondence. P equals delta P, a boundary. And if you know a little bit of rational geometry, you will see that this is a local Abijah structure on R. A phi, same thing as a local Abijah structure. And this maybe simple observation is the bridge between F-singularities and birational geometry. Because birational geometry is all about this sort of structures, boundaries. So that when you add them to the canonical divisor, something beautiful happens. Okay, and that's what phi is all about. So this is why we're going to try to understand F-singularities a little bit in these terms. So just to finish, again, it's having that F-singularities is really a theory of singularities because it is something about the canonical divisor. Properties about the canonical divisor deep down. Again, we'll do that next time, so let's stop here. Any questions? And just to be clear, all this I said in a rush, we're going to do it line by line next time.